6.5 is talking about power functions with negative powers, which we have discussed a bit in class. So this is probably not a new concept. A negative power of x, right? So if I have x to the minus p, where p is a positive value, then that's going to correspond with 1 over x to the p. So if, for example, I have x to the negative 2 power, that corresponds to 1 over x squared. And the same goes with x to the minus 1. That is just 1 over x. This is known as our reciprocal function, which we've worked with a bit recently. All of these functions are assuming that p is greater than 0, so that you have a negative power. And if you have a negative power, so it becomes a rational expression, then you have a 1 over x to something, which means that you have a problem if x goes to 0, because then you have a 1 over 0 scenario, which, right, we know blows up because f of x goes to plus or minus infinity if you divide by 0, because you can't actually divide by 0. This is something that we call a vertical asymptote, and graphically we'll play with them a bit more in the next section, but for right now, this is what it is. If it blows up, if you divide by 0, what you have is a vertical asymptote. We can actually give it a name now at the value when x equals 0. So what's happening with these functions depends on the function itself. So if we look at the reciprocal function 1 over x, as x approaches 0 from the left side, meaning from the negative side, f of x is going to approach negative infinity because, for example, a small number on the left side close to 0 would be negative 0.01. So if I take 1 over negative 0.01, I'm going to end up with negative 100, which is a large negative number. So I know that the closer and closer I get to 0, the more large and the more negative that value will be. So that's what tells me that as I approach 0 from the left, f of x will go to negative infinity. Conversely, if I approach 0 from the right side, then I have a positive value, so 0.01 for example. The function 1 over 0.01 will get me 100, which is a large positive number on the right-hand side. So my asymptote goes to negative infinity on the left and positive infinity on the right. If we graph it, which I highly recommend you graph 1 over x on your calculator just as a reference point also, you can see that it has this general shape that I've sketched in here. There's something additionally you can see. So there's a vertical asymptote when x is equal to 0, which corresponds to the y-axis. But there's also some end behavior here that's interesting. It's not what we were talking about in the previous sections where things were going to positive infinity or negative infinity. Now it's going to 0. Which is different. That's new. So as x goes to negative infinity, f of x is approaching 0. It's approaching the x-axis. As x goes to positive infinity, f of x is also approaching 0. Because effectively what ends up happening is as x goes to infinity or negative infinity, you're effectively dividing by infinity, which you can't actually do, but as the numbers get bigger and bigger and bigger, those expressions are going to go towards 0. Now this gives us something that we call a horizontal asymptote for the same reason that we call a vertical asymptote a vertical asymptote. It never actually reaches the y value that it's approaching. You can't plug in that y value and get something back, but the end behavior is approaching a constant. It's not going to infinity. It's going to some specific value, and that value is the horizontal asymptote. And because it actually has that, because it's going there, but it never actually equals that value, it's an asymptote. So we say that 1 over x has a horizontal asymptote at y equals 0. It has a vertical asymptote when x is equal to 0 and a horizontal asymptote when y is equal to 0. We apply this concept of negative powers of x through inverse proportionality. We talked a lot about direct proportionality before. So inverse proportionality versus direct proportionality. All right, direct proportionality is where you have a constant times the actual term. So Q equals K times R, where R is your independent variable, like your X, and Q is your dependent variable, like your Y. And so you put in the X, and that's directly proportional to the Y value because all you have to do is multiply by some constant. Inverse proportionality uses a reciprocal. So when I substitute in an R, the Q is proportional to that constant divided by the R instead of times it. So when R increases, Q will decrease, because if I divide by a bigger number, I will get a smaller number, and vice versa. If R is small, i.e. getting close to 0, Q will get very, very big, just like we were talking about and we saw in the graph. K is still the proportionality constant for this relationship, but now there's an inverse relationship instead of a direct relationship between the variables. So let's look at an example. If Q and R are inversely proportional, and Q is 2 when R is 5, what is the proportionality constant K? So we have the form based off what I said, what is above this question. We have the form that is Q is equal to K divided by R, and I was given Q as 2, and I was given R as 5, so all I have to do is algebraically solve for K. So I multiply both sides by 5, and that gives me 2 times 5 is equal to K, or rather K is equal to 10. These are the types of things that you're going to do manipulation-wise with these functions. If I give you specific application using inverse square laws, which takes it to another level, because instead of being just an inverse relationship with 1 over x, we're now looking at an inverse proportionality to the square of x. And then so generally we would talk about this as f of x equals k over x squared. And this models a lot of physical systems, actually. So we are going to just talk about one for this video, and that will be the intensity of light, where the intensity is equal to some proportionality constant k divided by x squared, where x is the distance you are from the light source. Now, given that you know this is the relationship, if you move twice as far away, how will the intensity of the light change? So x is going to 2x. How does that change I? So I substitute 2x in for x into the equation. K over x squared becomes k over 2x quantity squared. So I end up with this factor of 4. Since k over x squared was I, that 4 means that I have 1/4 of my original intensity. So if I move twice as far away, I have 1/4 of the intensity of the light that's coming at me from that source. We can ask additional questions like, if I know the intensity at a specific distance, then I can determine my proportionality constant. So if I is 200 watts per meter squared when x is 2 meters, then what is k? So 200 is equal to whatever that k value is divided by the distance 2 meters squared. So 200 is equal to k over 4. Multiply both sides by 4 to get 800 is equal to k. Now we have the constant, so we have the actual model for the light intensity. So I is then 800 over x squared. What is I then if you move to 5 meters away? So I substitute 5 in for x to solve for the intensity. 800 over 5 squared. 25, so 25 goes into 100 4 times, so what I have is 4 times 8, or 32 watts per meter squared, for the intensity of the light when I move to 5 meters away. Please let me know if you have questions, and we'll see you in class.